weekend nearly upon us. I am looking forward to, because no one will be having pizza. So, how are y'all doing today? Good? I'm glad to hear it. Things are, this is not a great project to read yet. News reading very quickly. Some good news at the very least. This is the last day where I am going to be presenting you new information that might be on an assignment. That means all of next week we're going to be going over all assignments, making sure everyone is up to speed on how the exam is going to work, where you need to be, what you need to do, and what will be on it. So, we're going to wrap up our learning for the semester, which means you will have officially survived physics. And all you have to do is make sure everything is passed in and take your exam. After that, you survive physics. We're going to wrap things up by talking a bit about some of the specific things that sound and light do. So these behaviors specific to each, and also a couple of the behaviors that they both have in common. One second. Now, before we get too far into things today, we're doing well. Does anyone have any questions, concerns, needs, etc. before we continue today? All right, let's get to it. So this is going to wrap up the things I think you should know about waves in order to exist as a human being on this planet. I believe we left off last time looking at wave speed, and as a general rule, every single kind of wave has some speed. That speed does depend on the product of the wave's frequency and its wavelength, but that speed also is going to depend on what type of wave it is and what that wave is moving through. For example, a very specific wave that we are all familiar with is sound. Sound is a mechanical wave, meaning it requires a physical medium. We, humans and our eardrums, are designed to hear sound in air because we live in air. We are surrounded by air specifically at all times. But sound can pass through a lot of different things, not just air. If you've ever been underwater, you've probably heard some sounds down there. Granted, it probably doesn't sound correct. It doesn't sound clear to you. I know when I was younger, my brother and I would play a game at the pool every so often where we'd just be standing right in front of each other. We would both go into the water. One of us would say something under the water, and when we came up, the other person would have to guess what they were saying. No one ever got it right because the human ear just isn't designed to work down there. But you can tell there's some sound getting to you through the water. And another specific example of sound waves traveling through a liquid is actually an ultrasound. We call it an ultrasound when someone goes in to see their unborn baby because we literally send sound waves into on the stomach, and the sound waves form an echo and bounce off, and that creates an image, kind of like how a bat can use sonar to detect things. So sound can travel through the solid and the liquid parts of a human's body, as well as the air around you, the water, if you are submerged in water, and also even travel through the ground. And the speed of sound depends on what it is passing through. We have here a table listing the speed of sound at through many different objects, some of which at different temperatures. The ones that you will interact with the most in your lives are these ones right here. This is the speed of sound in air. We have one speed of sound for air at 0 degrees Celsius, that's the freezing point of water, and one speed of sound at 100 degrees Celsius, that is the boiling point of water. Now, that does mean that the speed of sound does depend on the temperature of the thing it is passing through. And this is due to the fact that when a sound wave travels through the air, so what I'm drawing here are air particles. These are the molecules that make up the gas that makes up the air. When I speak, I am putting energy into the air. And when these particles have energy, they're going to start vibrating. They have energy, they begin moving. If I'm standing here, these particles will move on to strike the next particles and transfer the energy into those, and then they'll strike the next ones, and they'll strike the next ones, and that is how the sound travels through the air. It's just a continuous chain reaction, a sequence of collisions of the particles. And the warmer something is, the more its particles are already colliding anyway. So that helps to facilitate the sound traveling through it at a faster rate. In addition, you'll notice as we go from gases into liquids, most of these speeds tend to be higher than most of these speeds, even at a lower temperature. The denser the medium, the more dense the material that sound is traveling through, the faster it tends to go as well, because in a denser medium, the particles are bunched more closely together, which makes it a lot easier for this one to collide with the next one because they're closer together. So the collisions happen a lot faster, the energy is able to transfer from point A to point B a lot quicker. So, as temperature rises, sound speed increases. As density rises, sound speed increases. Which means that sound is actually typically fastest through most solid objects. There are some exceptions, but by and large, sound is fastest when moving through solids, next fastest through liquids, and slowest through gas. Which is a little inconvenient because we hear it through gas, but we can't breathe underwater, and we definitely can't exist inside of the solid earth, so we make do with what we got. Now, humans, at least here in South Carolina, we don't tend to live at these temperatures, so the speed of sound, I do think I wrote this on the board yesterday, but I want to further clarify. The speed of sound in air at 25 degrees Celsius, which is room temperature, that's the temperature you're feeling right now, is 343 meters per second. So this is considered to be a known constant. This number will be provided to you if you need it. And sound is pretty quick. Within 1 second, a single sound wave can travel the length of about 4 football fields, which is pretty impressive. But it's worth noting, again, I wrote this number up on the board too. The speed of a wave depends on what type of wave it is. So all sound in air moves at this speed, regardless of what pitch it is, or frequency, or even volume. Meanwhile, speed of light, all light, is 3 times 10 to the 8th meters per second, which is literally exponentially faster. Light is so fast, if an event takes place on planet Earth, all events involving the light will be regarded as instantaneous as far as the human brain is concerned. This is faster than the brain's processing speed. However, there are moments where we can kind of see sound lagging. Because light is faster, there's times you can see an event before you can hear it. Specifically, the most famous occurrence of this is thunder. Say it's a big stormy day, we've had a few of those recently, and off in the distance you see a lightning bolt, a lightning strike. Light is much, much faster, so you are going to see the lightning way before you hear it. Now we're going to consider that the light arrives at you basically instantaneously, because if you are close enough to see the lightning, you are close enough such that even though it might take the light a couple of nanoseconds to get to your eye, that number is going to be incredibly small versus the time it took the sound to reach you. So we're going to assume that the light from the lightning bolt reaches you basically instantaneously, but occasionally, depending on how far away the bolt is, it takes a couple of seconds for the sound to actually reach your ear. Granted, the closer you are to it, the louder and the faster you will hear it. If you see lightning and hear the thunder at the exact same time, run, because that storm's right on top of you. But most of the time, there's going to be a slight delay. And that delay can actually tell you how far away the storm is. So, for example, specifically, let's say that you are watching a storm, you see lightning, and then you hear the corresponding thunderclap 6.4 seconds afterwards. So, time, 6.4 seconds. The speed of sound in air, what we're going to be using here, is 343 meters per second, and we want to know how far away the lightning strike was. What formula do you think we should use?
E equals T times P.
One more time. You have V, D, and T. How do those all relate together?
Would it be D equals F?
It's okay. This is one of the first formulas we ever covered. The sound is simply moving. So, we know velocity, we want distance, we know time. How do those all relate together? Cast your mind back to many months ago. Yep. Sometimes something is just moving, that's all you care about. You can use this formula when something is moving at constant velocity, and we consider sound to do that in air. It has a constant speed. Sound does not accelerate. So, we're going to plug in our constant speed of 343. Put delta D over our time of 6.4 seconds. And if memory serves, please pull out your calculators to corroborate this. This should be about 2094.5 maybe, something to that effect. Please correct me if I'm wrong. I'm pulling this number from memory, not because I found it in my head.
It's 2,195.
195, thank you.
0.2.
0.2. Thank you very much. So, in conclusion, that is very far. You can detect a storm from very far away before it's actually in danger of, say, hitting a tree on your yard. But this is probably one of the oldest, literally one of the oldest tricks in the book. We've been seeing lightning for as long as we've been on this planet. And it's one I encourage you to recall, even if you don't take out a stopwatch to measure the time between the strike and the thunder. At least keep in mind, the bigger the gap is, the further the storm away. the further away the storm is, the smaller the gap you run. Yes.
So is the 1 second per mile thing pretty accurate?
1 second. Well, let's take a look. Did 1 second, and the sound would travel 343 meters. Let me convert that to miles real quick, because that's a number I don't have in my head. That is not correct, because 343 meters is only 0.2 miles. So it would be closer to 1 mile per 5 seconds.
It's a lot closer.
Yes. Yes, it is. Sorry, say again? Oh, to figure out miles? Well, the conversion between meters and miles is 1,609. Even I don't remember that number off the top of my head. I don't use it too much. But you can keep in your head, 5 second gap is 1 mile. Half of that would be half a mile. Okay. Oh. One more trick regarding sound. This is probably the second oldest trick in the book. We saw on the table that sound travels fastest through solvents. For starters, this is one reason why earthquakes are so dangerous, because a seismic wave is basically a giant sound wave traveling through the ground. And because it can travel so quickly through the ground, it can go from one end of the continent to the other in a stupidly short amount of time. Which is one reason why it was always very hard historically to figure out where an earthquake came from, because it seems like it's just everywhere at once. But now we can actually pinpoint like the tectonic plate of origin. But even older trick than that, because sound travels fastest through the ground, you can put your ear to the earth, and the ear is the part of your body most sensitive to sound waves. So if you put your ear to the earth, you'll be able to feel certain things approaching long before you would have heard them through the air. The two things that people most often use for this are to feel trains coming, either by putting your ear to the ground near the tracks, or I don't recommend this. Some people would just put their ear on the rail. Don't recommend this. Be safe. But the vibrations from the train would travel through the rail faster and more powerfully than they would through the air, so you can feel it coming a lot sooner that way. Also, people would do this to tell if there was like a stampede coming. I don't think it shows up as much in media, but I definitely saw some westerns where people use this. So, those are the specific idiosyncrasies about just sound. We're going to transition into looking at some of the things about just light before ending on some of the things that they have in common. Any questions before we switch into light? Okay. So, first, the ways that light is different to sound. Sound is a mechanical wave. It requires a physical medium. Light doesn't, because it can travel through the vacuum of space. If it couldn't travel through space, then we wouldn't get any warmth or energy or light from the sun. So light is a very different kind of wave. It is an electromagnetic wave because it is made up of energy, electricity, and magnetism. Light is very, this is me speaking to you as a physicist who has studied this. Light, technically speaking, is weird. We're still not entirely certain what it is and everything that it does, because we can't actually grab it and study it. If you were able to isolate like a single piece of light, like you were able to isolate a single proton or a single electron, you could grab just one light particle. We call that a photon, but photons are not solid objects, so we can't grab them. We also can't actually see individual photons. You in this room, you're seeing lots of things at the moment, but can you tell me, what photon is where? The human eye is not built for that. What you see is the light that bounced off of things. You can't detect the photons directly, which just makes studying light even harder. In order to actually study it, we have to look at the things that it does. And so the next couple slides are going to be the list of things that we do understand about light, simply because we have observed it do this stuff in relation to other objects. We know that light is electromagnetic in nature because the various ways that we have made light and other electromagnetic waves involve electric and magnetic forces. Our best guess, our best assumption that all of our math seems to validate is that light is actually made of an oscillating electric wave and a magnetic wave traveling together at once. But light is essentially just traveling energy. This is how the energy is traveling. And again, you can't ever see this, so that's just one of the tricky parts. It is a wave, it acts like a wave, but it also has a couple of properties similar to particles. When I say particles, I mean like protons and electrons, which just makes light even weirder. There's a lot of people in academia arguing about what light is and how we should treat it. So this is the weird stuff. This is why we don't fully understand what light is. This is the things that we do know about it, just because we've observed these behaviors. We know it behaves like a wave. It has wave-like properties. It has a measurable frequency and a wavelength. For sound, frequency determines pitch. For light, frequency determines color. Oh no, there was one more sound thing I wanted to mention. You guys okay if I backtrack for a second? Okay. I feel like this is important because it involves your ability to hear. Okay, all sounds have a frequency, right? Every single one has a different pitch. There's only certain pitches that the human ear can hear, though. You know how dog whistles hurt dogs but not people? Because dog whistles make a frequency of sound that humans can't hear but dogs can. So, the range of human hearing, the list of frequencies that we can hear with our ears, is 20 hertz to 20,000 hertz, which is a pretty big band, but the hearing range of a dog is 40 hertz to 40,000 hertz. So any sound between 20 and 40,000 is that high-pitched range that a dog can hear and we can't. But there are about 20 different frequencies between 20 and 40 hertz that we can hear that dogs can't.
That's crazy, because you can hear it across our head with a dog.
Granted, most of the sounds on Earth that we're aware of fall within this range. There's not a whole lot that goes on above this that we're aware of. But, yeah, well, on top of being able to hear more frequencies, dogs just have sharper hearing, period. And better smell. And better sight and sight sounds. But, the issue with this is the best possible range that a human can hear on the day that they're born. every second you are alive after birth, this top number starts going down. As you age, the cells in your ear divide, and they will never be as functional or pristine as they are the moment you are born. I, late 20s, and person who has been blasting music into his ears via a headset for most of my adolescence to adult life, my maximum hearing range is decreased to 16,000 hertz. You guys, if you've been taking care of your ears, might be about 18,000 hertz. As you age, you just lose the ability to hear these upper sounds. But again, most sounds a human regularly interact with are between 20 and about 10,000 hertz. So the elderly don't really, it's not like there's an alpha predator that the elderly just can't hear anymore. It's not like there's a wolf that only makes high frequency noises. I can only assume, I would assume that is just a property specific to ears. Although, if there was one creature that wouldn't affect, my best guess would be lobsters. But that's a bio fun fact. That can come up later. So as you age, this number goes down. Also, if your ears are damaged, this number goes down. And yeah, there's sounds you can hear that I can't. There's sounds both of us can hear that my grandfather can. And it's not because he's deaf. Pop has good hearing for his age. But there are some grocery stores who have utilized this. They install speakers that play high-pitched, whiny noises that teenagers can hear, but that the elderly who come in on like Wednesdays can't. And it keeps teenagers from loitering outside the stores.
What?
Yes.
Wait, say that again?
Because teenagers can hear really high-pitched noises that the elderly can't, grocery stores, some of them will install speakers like on the front of the building that play those high-pitched noises so that teenagers are less encouraged to just hang out in front of a grocery store or loiter or do whatever it is youths do that the elderly don't like. Probably skateboarding.
Oh, I've heard that before. I've been going through like the doors. Oh yeah, like I always thought it was like the way that sensors and stuff work. Like when you're walking out of like a sliding glass door. Is that, it's not like...
I'm not sure where they install it, and I've never heard it. I don't recall having heard it. Maybe it's because by the time they became commonly used, I've already lost the ability to hear it. But specifically at my high school, after I graduated, they built a food line across the street. And for some reason, every student wanted to go hang out at the food line because there was food there and because it wasn't school. And they had to put those in to keep the teenagers from just standing around and, I don't know, being young and scaring off the paying customers. Because, I don't know, youth is money, youth repels money, I don't know. But I feel that is important. Take care of your ears, and this is probably one reason why old folks don't like the music the kids are listening to. Now, back to light. Light has a frequency, a wavelength, it engages in later behaviors, and we know its top speed. I tend to round this to 3 times 10 to the 8th. This is the number you need to know. This, don't worry about this part. This is just how that number was calculated. Thank you, Einstein. And because this is a universal constant, it does have a variable. This is c, lowercase c. And this is actually the same c in E equals mc squared. So that c is the speed of light. Oh, the 3 equal signs mean is defined as. So the speed of light is defined as this. These variables talk about the maximum speed that something can move through the fabric of the universe. These get used in more upper level physics. They relate to the very nature of the medium of space itself.
I thought I knew something. I was thinking constant, that would help.
Oh, okay. Well, these are, I don't remember which one's which, these are the permeability and permittivity of free space. And they specifically have this little zero next to them to distinguish them from friction and from whatever you put a number in. So this number is important, but it'll be given to you on formula sheets. It's a known constant, and I don't hide those from you. Now, light is an electromagnetic wave, but it's not the only kind. Every type of radiation is the same thing as light. You have an entire band of things, an entire family of different types of electromagnetic radiation that form the electromagnetic spectrum, of which light is simply a piece. The human eye can only detect a specific frequency of radiation. Everything else is invisible to the human eye, but has very different properties based on its frequency. All of these are the same kind of thing, they just have different frequencies. So, the members of the electromagnetic spectrum, the types of radiation that we know of that exist are, at the lowest frequency, highest wavelength end of the spectrum, we have radio waves. These are the weakest kind. And these are the kind that your cell phone and Wi-Fi, every kind of wireless communication that humans have use. So literally your phone is putting out radiation right now because radio waves are a form of radiation. We use radio waves for this purpose because they are harmless, at least to humans. Sorry, they are harmless in general. They do nothing to an organic being because they have a very low frequency. The danger level for an electromagnetic wave tends to increase with its frequency. This is the low side for frequency. So radio waves have the lowest possible frequency of all electromagnetic waves. That makes them harmless. They will pass through a human body and do nothing. So we use them for communication. There's probably thousands of them passing through you right now from the Wi-Fi, from every cell phone in the room, from actual radio broadcasts. They're fine. Nothing's ever going to happen to you because of a radio wave. But if you increase the frequency on radio waves, not actually labeled up here, I apologize for that, but right about here, the highest frequency radio waves gain enough energy to be considered a different type of wave. They are microwaves, like the appliance in your kitchen. The machine called a microwave uses a microwave radiation that it literally blasts your food with radiation to make it warmer. This type of radiation does not make things radioactive, so don't worry about nuking your food. The main properties of microwaves are that they only heat up, and they only heat it up, they don't radiate, sorry, they don't make it radioactive. They heat up water and metal. This is why you don't put a fork in the microwave, because the metal of the fork will go ballistic when you blast it with microwaves. Food is all water-based. Pretty much everything humans eat has water in it, which is why the food heats up in a microwave, but it's probably why it gets really sizzly and steamy in there. It's only heating the water, and then the water heats everything else up afterwards. But because it only heats metal and water, the glass plate or the glass mug that you put in there with it doesn't become scorchingly hot because it doesn't have any water in it. If you turn the microwave on with just a ceramic mug in there, you pull it out and it's probably the same temperature. Only water and metal. And we discovered microwaves on accident because, again, we use radio waves for transmissions. So some military scientists decided, well, what if we crank up the frequency and use whatever is in that band as super secret military communicating that no one else knows about. So they cranked up the frequency on their transmitters, their dishes started putting out microwaves, and all their machinery fried because it was all made of metal. So they failed to make stealth communication, but they did make a way for me to warm up noodles.
Yes.
So, again, as you increase frequency, things tend to get more dangerous. After microwaves comes infrared. This is basically just red light that can't be seen by humans. There are other animals that can see it, like bees and mantis shrimp, but this is out of the range of detection for the human eye. But it is basically just invisible light. It acts more like light than it does anything else. Yes?
Isn't this how they like figured out or like confirmed the Big Bang? Like they found like the redshift light or something like that?
That is due to this and the Doppler effect. Granted, it's all still a hypothesis, but you are right. Some scientists have looked at the shift in the frequency due to the speed of the universe to figure out how long ago something must have originated. We use infrared for various things, like when you need to use light for something but you don't want to be able to see it. But if you increase the frequency past infrared, you will hit the visible light spectrum. So if you're looking at like something emitting infrared and someone increases the frequency slowly, you'll eventually see normal red. In general, red is the lowest frequency that you can see, and violet is the highest frequency you can see. These numbers up here correspond to wavelength, which goes through the inverse process. As frequency rises, wavelength drops. And if you crank up the frequency past violet light, you get ultraviolet light, which is just violet light that we can't see, but that bees and mantis shrimp can. And remember again, as you increase frequency, things tend to get slightly more dangerous. This is where the radiation can start damaging human cells. Granted, ultraviolet light is just the part of sunlight that sunburns you. UV, all it can do is sunburn you. Maybe give you skin cancer in high enough doses, but it's the tamest of the ones that can damage your cells directly. Well, I guess microwaves don't stand the microwave. If you crank up the radiation past UV, you get X-ray. You're getting into the territory now where the waves can pass through your whole body again, and X-rays have enough energy, they're high enough frequency to do damage to cells when they do so, but only in high doses. When you go get an X-ray at the doctor's office, they are shooting X-ray radiation through your body, but it's calculated to be in such a small dose that it doesn't hurt you. The X-ray technician only runs to the county over and puts on a lead vest because they're doing this repeatedly. They are the ones being constantly exposed to the radiation. They need to be the ones protected since they're doing this 18 million times a day. But if you go to the patient, it's calculated so you'll be fine. Then crank it up past X-ray, you get gamma rays, and this is what makes the Incredible Hulk. This is the dangerous stuff. This is what most people think of when you say radioactive. It's the highest frequency radiation that is naturally encountered on Earth. There's probably some higher frequency ones in space, but yeah, it's basically just super gamma. And this is dangerous because not only can it go through your entire body, it carries the most energy and is most likely to damage something on its way out. When you think of like radioactive waste, it's giving off gamma rays. But not all gamma rays are 100% awful all of the time. Right now in this room, you are being irradiated. There is radiation around you all the time right now. Like I said, there's radio waves, there's light, but there is also gamma rays in this room. The human body makes gamma rays. Everything naturally goes through radioactive decay processes, if you've studied chemistry. The calcium in your bones is one of the densest and most radioactive parts of your body, and it breaks down at such a rate that you produce from your own body 1 gamma ray every second. So from yourself and from the humans around you, you are being irradiated right now. And you're fine. The human body, we've yet to figure that one out. Hulk already violates several laws of physics. I don't know if we need that right now. Your body is used to a certain amount of gamma rays since you make it, and since we have to interact with other humans who also make it. The danger with gamma is only if you go over a certain danger threshold. Like most things, it's only poisonous if you take too much of it. Like venom or pizza. All things are more dangerous in high doses. Back to light for a second. This is again the band of frequencies that you can see. And I want you to notice the order here. This is Roy G. Biv order. And this order is the reason why the sky is blue. Our sun gives off every color of light, but some more than others. All stars give off different amounts of each color based on how big they are, how old they are, what they're made of. Our sun gives off some of all of it, but not much green and mostly blue. So when that light hits our atmosphere, the atmosphere sort of acts like a prism and scatters the light into its colors. But the atmosphere also starts absorbing the energy of the light because it's now passing through light, it's passing through matter, and its energy is naturally going to be absorbed by it. This is how we get warmed by the sun. And the color, it starts absorbing the colors in reverse order. The atmosphere chews through the violet, chews through the indigo, and in the day that mostly leaves blue. So the sky is blue because of our sky and because of the specific star that we orbit. But the sky changes colors at sunset because of midday, Earth is here, sun is here, and you've got this much atmosphere to get through. At sunset, the geometry changes and you've got more atmosphere to pass through to get to the same spot on the planet. That means the light goes through more air, and the air is going to chew up even more colors until you only have these ones left. Which is why sunrise and sunset are these colors, and midday is this color. You never see green because the sun barely gives off any green light, but if you're watching the sunrise or the sunset very closely, you might be able to see the second where it's done chewing through the blue, and you can see the green for just a second before it goes away. Sailors would call this the green flash, and they would use it to tell time. This is also why plants are green, because they want to reflect the green light and absorb the rest of it. Since there's just very little green, they want to reflect the thing that there's blue stuff and absorb the rest. Just find how interconnected this all is. It's very cool. Okay. Last couple of things. These are just 3 concepts that I want you to be aware of before we break for today. Again, we can't really see waves directly. We only see what they do. And we're about to talk about 3 specific things that waves do when they hit something. Because oftentimes we can only tell a wave is present when it hits something, and then one of these 3 things happens because of it. The first thing waves can do when they hit something, and this counts for both light and sound, is reflect. Light bounces off of things. Sound can too, we call that an echo. But when light does it, it forms a reflection. And you've observed this. Light will bounce off at the same angle it approached at, which is why if you want to see yourself in a mirror, you stand right in front of it. But if you turn and you're sort of like at a 20-degree angle, you'll only see what's 20 degrees away from the mirror in the other direction. Now, all objects reflect. This is not just mirrors. So if light is reflecting off of this cinder block, why can you not see a reflection in it? It's not glass, it's not polished, and it's not smooth. Light bounces off at the same angle it comes in at, which means if your surface is rough and bumpy, the light's going to scatter into a bunch of different directions. But if something is smooth on the molecular level, all of the incoming light will bounce off in the same direction, and you can form an image of whatever's over there over here. This is the difference between a mirror and everything else. which is usually why when you polish something to make it shiny and make it reflective, you are literally smoothing it out. The next thing that waves do when they hit something is they, instead of bouncing off, they can go into it and pass through it, like when light travels through glass or through water. But when waves do this, things tend to get a little weird. Have you ever looked at a glass of water and noticed something like this? All right. This is the principle of refraction, and when a wave enters a new medium, it tends to bend slightly. It changes direction. Sort of like if you hit something when you ran into it, you're probably going to shift in your path slightly too. So you can see, like, the camera's in air, so this part is normal, but the light from this part has to pass through the water back into the air. It's going to bend when it does so. You might have seen this again with a glass of water. You might have seen this in the pool. I know when I was a kid, I would put my hand in the water, and even though I'm putting it straight down, it kind of looks like it's curving off to the left. But a very egregious example is this guy. I promise he's not decapitated. It's just a trick of the light. He's fine. Look, he's smiling. Now, this is convenient because it's the reason glasses work. A lens uses the principle of refraction to bend light and put it into the right spot. If you need glasses, it's because your eyes are probably the wrong shape, and the image formed by the lens of your eye, like the lens on the front of your eye, isn't putting itself on the right spot of the back of your eyeball for your brain to perceive it right. So the lens of your glasses bends that spot, bends the light so that it forms in the correct spot in your eyeball, and then you can see correctly. So refraction does weird things, but it also does some very convenient things. It's also the reason why prisms work, because all light will bend when it enters a new medium, but each color sometimes bends at a different angle, which has the tendency to separate white light back into its colors, like what the atmosphere does when the sun enters it, or specifically what water droplets do in the sky when they form rainbows. So, in short, the principle of refraction is responsible for this weirdness that you've observed. It's responsible for your glasses working, and it's responsible for prisms and separating light into rainbows. And the very last thing that waves can do when they hit something is be absorbed. When light hits you and you are warmed by it, it's because you absorbed it. You now have that energy in your body. It didn't bounce off of you. This contributes to how we see, because like the sun, these lamps are giving off every color of light, but only the orange light bounces off of my shirt, which is why you see orange when you look at it. Every other color was absorbed by my shirt, so that only the orange bounced back off. Which again is why plants are green. They want to absorb as much sunlight as possible, so they are the color that there is the least of in sunlight, so that they reflect the tiny little bit of green and absorb everything else. I'm wondering if the leaves change color in the fall because they need less energy, or if it's just because the leaves, that's just what happens to the chlorophyll when it dies. So, that is, I feel, everything that you should know about waves to exist as a human being on this planet. And that is all of the new learning for this semester. You have survived physics. Now all that's left is studying and the exam. Thank you all. It's been a great semester, and I'm going to help you see it through to the end. We're all going to finish well and do well. If you have any questions, please don't stick around to ask them. But if you don't, have a wonderful day and have a wonderful weekend. We'll be back here next week to talk about the test we just took, the first test, and make sure everyone's clear on how the exam's going to work, because here or aren't here when I describe it, and everyone needs that information. I'm going to repeat myself a lot. Thank you all.